So, good morning, everyone, and thank you for attending this session. My name is Aditya JADHAV, and today I'll be presenting our work title Using an Ensemble Approach for Layout Detection and Text Extraction from Historical Newspapers. This work is in collaboration with my colleagues, Professor Bipasha Banerjee and Jennifer GOYNE from the University Libraries at Virginia Tech. Here we have included a QR code that links directly to the digital library website maintained by the Virginia Tech University Libraries. If you are interested, I encourage you to explore it. It contains a rich collection of archival material, including the Montgomery Museum newspapers that we use in this work. Moving forward, this is an overview of topics that I'll be talking throughout the presentation. Uh, let's start with the motivation. So, historical newspapers pose fundamental challenges for machine understanding. Unlike modern documents, historical newspapers exhibit extremely complex and irregular layouts, including multi-column text, ornate headlines, advertisements, halftones, and illustrations. Additionally, the physical degradation present in many scans, such as bleed through, skew, uneven illumination, and low contrast, compounds the difficulty in layout segmentation. Commercial OCR systems like AWS Test Track do offer a baseline, but they become increasingly expensive at collection scale. Moreover, importantly, they are difficult to tune, and their proprietary nature makes limits reproducibility, which is critical in archival context. Finally, single detectors, deep learning detectors, even powerful ones, tend to fail in this domain because they are asked to reason about text, halftone, borders, and decorative structures all at once. These complexities motivated us to pursue a layered ensemble style approach that divides the problem into more manageable parts. So prior work on layout segmentation suggests that accurate layout segmentation is critical for downstream OCR tasks. Moreover, studies on this show that when segmentation fails, OCR quality drops quickly. Existing methods span from rule-based techniques like threshold-based binarization, connected component grouping, and geometric-based heuristics for separating text and non-text regions, to recent deep learning detectors like faster RCNN or YOLO variants, which are trained on datasets like PubLinet. A consistent theme that we observed is that no single detector is robust across the full variability of historical newspapers. This observation forms the conceptual basis for our ensemble pipeline. Commercial OCR platforms like AWS TextRack, and Google Document AI deliver end-to-end workflows, but their closed models limit tunability and their per-page pricing restricts use in large academic collections. On the open source side, frameworks like Layout Parser, Prima evaluation tools, and the more recent vision language models support reproducible OCR workflows and achieve strong results on the noisy historical scans, but they rely on well segmented input regions. So when these models are shown a full newspaper as an input, the generated text often becomes less accurate. There is limited work on integrated multi-stage ensembles that bring together rule-based filters, document-specific detectors, and LLM-based OCR in a unified reproducible pipeline. This gap directly motivates our research goal. So the central goal of our research is to develop an open, detector-agnostic pipeline pipeline for extracting layout and text from historical newspapers at scale. We present three primary contributions: layout at first, iterative workflow that separates layout detection from text extraction, improving stability on highly variable pages. Second, a multi-layer layout recovery process using OpenCV, newspaper navigator, and a fine-tuned text-only Prima model. And lastly, a dedicated text-only detector fine-tuned on the Prima dataset, which addresses the limitations of generic multi-class detectors and produces clean, tight bounding boxes even on degraded scans. Together, these contributions produce a robust alternative to single detector pipelines. Moving ahead, so our dataset consists of digitized newspapers from the Montgomery Museum in Virginia. These scans span several decades and include multiple local titles. The pages exhibit substantial variation in layout as well as in the digitization quality, because the collection combines flatbed and camera-based scans. We encounter when we encounter all major forms of historical degradation, bleed through, noise, uneven illumination, and varying gutter widths. The high layout variability makes this collection an ideal benchmark for robust layout detection. Now moving on to the methodology section, this is the AWS baseline architecture. Before moving into our open source workflow, I'll explain the AWS architecture briefly. We structured this workflow into three asynchronous phases. So the first phase performs layout detection, the second phase performs text extraction, and the last phase generates metadata such as confidence scores for the line and word level predictions. This baseline allowed us to understand reading order reconstruction and manifest generation. It also offered us insights into the strengths and weaknesses of a commercial worker serverless workflow. We, however, we encountered three major limitations. Uh, First is the high per page cost. Second, limited tunability, especially which is especially problematic for noisy or irregular pages where we need to control thresholds, and lastly, small variations across runs, which makes reproducibility difficult. These limitations motivated us to move from TextRect and towards a fully open detector agnostic pipeline that we could tune, audit, and reproduce. Now that we have looked at the AWS baseline, let me walk you through our open source workflow. In this slide, I will give a brief overview of our open source workflow. And then in the next consecutive slides, I'll go through each component in much detail. So as you can see, our pipeline is divided into two main phases. One is layout detection, and the phase two is text extraction. In phase one, we use an ensemble of three detectors: OpenCV, Newspaper Navigator, and our fine-tuned text-only Prima model. The ordering of this ensemble is intentional. Starting with a rule-based OpenCV layer helps remove high-confidence rectangular panels and reduces clutter early, which simplifies the later models. After OpenCV crops out the detection blocks, the remaining residual page goes to the Newspaper Navigator, which focuses on detecting the large non-text elements, and then to a text-only primer model, which recovers tight, stable text regions. All the detected regions are then cropped and stored, and these segments are then passed to the phase two, which is the text extraction phase, which uses the Olmo OCR model and reconstructs the articles. This layered structure allows each detector to specialize in what it does best, making the pipeline far robust than relying on a single model. Let's go into detail on each one of these components. So the layer one is our OpenCV layer. This is what we call our precision first pass. The goal here is to remove only the most obvious high confidence structures on the page. Things like framed advertisements and large rectangular blocks without risking damage to the text. So here we deliberately use simple rule-based image processing techniques that gives us a high level of control and avoids over segmenting the page. We begin by normalizing the page. We convert it to grayscale and use auto thresholding. This automatically finds the best cutoff to separate ink from the background, even when the page has uneven lighting or faint print. This gives us a clean binary image to work with in the coming steps. From here, we run two parallel pre-processing paths, each designed to capture a different kind of layout feature. The first path looks for large rectangular shapes. We use CLAHE for this, which stands for Contrast Limited Adaptive Histogram Equalization. This method enhances local contrast, so dark regions stand out even on washed out scans. The second path focuses on finer details like gutters and separator lines. We use black hat filters, which highlight thin dark lines, exactly the kind of lines that separate newspaper columns. Once we have these two processed paths, we merge them and identify the connected components, which are essentially clusters of pixels that form meaningful shapes. For each component, we measure simple geometric properties like size, shape, and edge structure. Now that we have got these measurements, we score each component and keep only the ones that have high confidence scores. We crop these cleanly from the original page, and whatever remains on the newspaper is called as the residual page. This residual page is much simpler and it becomes the input for the layer 2. By removing large obvious structures early in this stage, we reduce clutter and make the later layers much more stable. So the next layer is the newspaper navigator. The residual image from layer 1 is passed into this layer. This model is specifically trained for historical newspapers, so it outputs bounding boxes for elements like advertisements, illustrations, headlines, maps, comics, and other non-text categories. During our experiment, we found that photograph detections often overlap with adjacent or surrounding text content. Photo boxes tended to extend slightly into the paragraph boundaries, and removing them immediately caused accidental removal of the nearby text. To address this, we adjusted the pipeline so that the photographs are collected but not removed at this stage. They are handled later once we have tighter, more reliable text detections. This small change helps us preserve boundary text and significantly improves downstream OCR accuracy. Now, for each accepted detection, we extract the crop and record its region coordinates and class labels. These regions are normally removed from the residual page, which helps clean up the clutter before the text-only model. The resulting residual image contains mostly text-like regions along with photographs that we intentionally deferred in this phase. This cleaner residual becomes the input for the text-only detector in layer 3. So going on to the layer 3, this is the text only primer model. The third layer receives the residual image that has already been cleaned by the OpenCV and the newspaper navigator layers. At this point, most graphical elements are gone. So this stage focuses entirely on detecting text. For this, we use our text only primer model, which is a detectron to generalized RCNN with a ResNet 50 backbone that we fine-tuned specifically to detect only text regions. We trained this model using the primer layout analysis dataset. Prima is particularly useful for this stage because it contains high quality text annotations that makes it an ideal fit for training a text only detector. Since the model learns to focus exclusively on paragraph structures, headlines, captions, and other textual regions without being distracted by the non-text components. The specific fine tuning configurations are summarized in the table on this slide. So with the earlier layers removed, removing most clutter, this text-only detector produces tight, stable bounding boxes that reliably isolate paragraphs, headlines, and small text fragments on degraded archival scans. Now, moving on to our phase 2, which is the segment level OCR extraction. In this phase, we take the regions detected from the layout stage and treat each one of them as an individual unit. Each crop is sent to the Olmo OCR 7 billion model using a very simple verbatim copy prompt. Running OCR on small clean segment gives a major accuracy boost compared to a full page OCR. Because each region is already isolated and stable, we avoid problems like bleed through, halftones, and the general clutter that confuses OCR models on full newspaper scans. Finally, once all the segments are transcribed, we construct articles by grouping regions and ordering them based on their geometric alignment. This produces a clean reading order and ensures that the final output reflects the natural structure of the original page. Now moving on to the results. So the AWS tech stack delivered consistent line and word boxes and performed well on clean pages. However, the region level segmentation struggled with degraded scans and irregular density, often merging columns or producing incomplete regions. These outcomes reinforced the need for having a multi-stage pipeline. Moving on to the results from the OpenCV layer. So as the figure illustrates, the OpenCV layer's ability to capture strong rectangular regions cleanly. Gutter structure is preserved here, and only the high confidence blocks are extracted in this layer. This establishes a reliable starting point for the subsequent layers to come. In the layer 2, like this slide shows navigator detections on the residual image. Advertisements, illustrations, and other non-text visuals are accurately separated. The clean residual at this stage becomes significantly easier for the text-only detector to interpret. Now moving on to the results of the layer 3. Here you can see how the fine-tuned text-only model detects tight, well-aligned text regions even in dense or degraded areas of historical newspapers. This layer directly addresses the limitations we saw in generic detectors like PubLinet, which often produce loose, overlapping boxes or merged entire columns. To quantify this improvement, we evaluated the model on Primatex dataset using the standard COCO style metrics. The model achieves a mean average precision of 76.7% with an extremely strong AP50 of 95.9%, which means that the detected boxes almost always overlap correctly with the ground truth regions. We also see consistent performance across object sizes. Together, these results show that the text-only model provides the stable, high-coverage text regions we need before passing the segments to OCR. This layer is what makes the downstream article reconstruction and segment-level transcription much more reliable. So, shown here is a sample of the OCR output for an advertisement region. The transcription preserves line breaks and punctuations. Because the segments are small and well defined, the Vision LLM model avoids hallucination and maintains originality to the source image. Finally, to conclude, our layered geometry-aware pipeline demonstrates that combining rule-based filters, specialized detectors, and Vision LLM OCR yields more stable and accurate results than single model approaches or text-tracked alone workflows. This modular design supports reproducibility, tunability, and large-scale reprocessing. In future work, we plan to introduce a page quality classifier, conduct formal benchmark evaluations, and automate end-to-end workflows for scalable ingestion in digital libraries. So thank you so much for your attention.